Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back again to this online structural geology course under NPTEL, and today we are at our lecture number 11 and we are studying rheology. Today we are at our part 2 of rheology lecture. In the last lecture, lecture 10 of rheology, we learned the three end members of rheology: elastic rheology, viscous rheology and plastic rheology. And today we will learn combined or complex rheology. So, in this lecture we will cover rheology of rocks as combined viscous and elastic materials. So, we will call it viscoelastic rheology. Similarly, we will combine elastic and plastic, that would be elastoplastic rheology. We will combine viscous and plastic, that would be your viscoplastic material. And then in the next lecture, we will cover some examples of the applications of rheology in structural geology, tectonics and geodynamics. So, we start with first the viscoelastic rheology, but before that let us have a look that what are the different applications of this combined rheology. So, in aquifers and reservoirs, so flow of groundwater and hydrocarbons, to understand their flow behavior, flow mechanisms, it is important that we use a complex rheology or combined rheology there. Magma flow in volcanic conduits, that also requires complex rheology to explain the flow mechanisms. In geodynamics, there is mantle convection, plate motions, the deglaciation phenomena, all these are explained by complex rheology. And if we come to the crustal deformation, the structures we generally see in the field, the ductile structures, folding, shear localizations and also earthquakes which are not ductile, but these are all explained by complex rheology. So, you can consider that almost all ductile deformations and their flow processes in earth can be explained by using the complex rheology. So, the complex rheology or combined rheology basics is very simple, that we will see that elastic, plastic and viscous, be it linear or nonlinear, these are often found to be too simple to model and explain the deformation behavior of rocks under certain conditions. So, it is important that we combine these three types of basic rheology in order to describe the natural rock deformation. And the combinations, the possibility of these combinations are many. So, as you can see here, I have added a spring and a dashpot, then I have springs of two different properties and then a dashpot, then two different springs, two different dashpots. So, you can array them in parallel and series and then again parallel and series and so on. So, what we are going to learn today is the very simple combinations in parallel and also in series, particularly for viscoelastic rheologies, and then we will see how to explain what would be their stress strain curve, what would be their stress versus time, strain versus time curves, and why these are important for understanding better the deformation of rocks. So, we start first with viscoelastic rheology. In the previous lecture, we learned that elastic behavior is not time dependent, that means it does not depend on time, and we also learned if we consider viscous rheology, then it is time dependent, it is strain rate dependent. Now, if we have to combine these two observations, that one rheology elastic is time independent and another rheology viscous which is time dependent, how can we explain this in terms of, or how can we apply this in our earth systems? Now, the general observations that we have seen from different type of long term or short term measurements, that crystalline solids, when it deforms, it behave as a viscous fluid in geological time scales, like 10 to the power 12 seconds or so on. But the mantle behaves as an elastic solid on time scales when it is very small, so 1 to 10 to the power 4 seconds. But it shows a viscous behavior on time scales when it is very high, 10 to the power 11 or 10 to the power 17 seconds. So, in general, if we try to understand that if the deformation is short timed, then the rocks respond as elastic manner, but if it is very long time, then it responds as viscous manner. So, this is a spot or this is a range where we can apply the viscoelastic rheology, the combinations of elasticity and viscosity. We combine them together in different ways, and then we can apply this viscoelasticity to explain the behavior of the deformation. And the materials that do have the property that in short time scales they behave elastically and long time scales they behave in viscous manner are known as viscoelastic material. So, let us have a quick review of what we have learned for viscous and elastic rheology. We know that elastic rheology is explained by a spring and the stress strain curve is like linear, something like that. This is your stress, this is your strain, and this is the stress versus time and strain versus time response, this one and this one. Whether viscosity is explained by a dashpot, and then here we generally explain it stress versus strain rate curve, and it is like this for a linear viscous material, and this is your stress versus time and strain versus time curve, where time is corresponding to stress and strain. Now, you can combine these two rheology either in parallel or in series. When you combine them in parallel, we see a different behavior. When you combine in series, we get a different behavior, and both of them have applications in structural geology or in geodynamics in general. So, let us first have a look. The first viscoelastic component that we will be talking about is known as Kelvin rheology. So, in Kelvin viscoelastic behavior or Kelvin viscoelastic materials, the deformation process is reversible, right. That is the first thing to get, but the strain accumulation and recovery are extremely slow. It is not like elastic materials, and this typical rheology, this Kelvin rheology, is also known as formoviscous or Voigt rheology. Now, generally this Kelvin rheology is explained, or we model it when we add spring and the dashpot, that means elastic and the viscous in parallel arrangement. What we see here, that I have spring and in parallel I have a dashpot. Now, the first statement that we made in this slide, the deformation process is reversible, you can clearly figure out if we stay within the elastic domain of this spring, does not matter how far I stretch this, it has to come back to its original position because there is the spring. So, this response of viscous part is important in determining that how much time it would take to come back to its position, because when it comes back to its position or when it responds this way, it is not a function of the spring anymore, it is a function of how much this fluid is allowing this entire system to come back to its original position. So, both systems in this case, the spring and this viscous dashpot, they move simultaneously under stress, but the dashpot retards the extension of the spring. Okay. So, when the stress is released, the spring will return to its original position. It will try to return to its original position very quickly, but again the dashpot will retard this movement. Okay. So, therefore, the deformation is time dependent, though the entire deformation is recoverable. So, you can again see this with the stress versus time and strain, I am sorry, this is stress, and strain versus time plot. The application of stress is very similar that we have applied to our elastic elements. So, we apply instantaneous stress, which is here to here, and then leave it for a while and then release the stress instantaneously, and then it stays at 0. But the strain response is very interesting. So, when the stress is 0, the strain is 0 at the beginning, but when we instantaneously apply the stress, now because it has both spring and dashpot in parallel, the strain increase is somehow non-linear, even if the spring is linear and the fluid here is a linear viscous fluid, because we are combining them. And once we release the stress, again the recovery is non-linear and time dependent. So, it comes back to its original position in an asymptotic manner, and this part, this release of strain very slowly, is known as viscous relaxation. Viscous relaxation has many applications in structural geology and geodynamics. We will not go into that part, but you just remember that when you are dealing with this kind of rheology, Kelvin rheology, then the release of strain after the load is gone is nonlinear, and it is extremely slow, and it is known as viscous relaxation. So, clearly I have the equation for this spring known is Hooke's law, and viscous is also known is the flow of the Newtonian, but because they are parallel, so the total deformation would be following the equation of parallel combinations of elements. So, if I have to go with the strain rate, so I know that 1 by strain rate should be equal to 1 by strain rate of the elastic element, which would be added with the inverse of the strain rate of the viscous element. And if we expand this equation or resolve this equation, then we simply get this equation where your total stress is equal to strain multiplied by the elastic element, and then viscosity multiplied by strain rate of this viscous element. And this is how, so this is Young's modulus and this is viscosity. So, this is how we explain the Kelvin rheology, where the strain is recoverable or the entire deformation is reversible, but the entire process is extremely slow. What would happen if we add this elastic and viscous elements instead of parallel, if we add them in series? Then what we get is known as Maxwell rheology. So, here we have the viscous element, here we have the elastic element, and they are added in a series. So, a Maxwell viscoelastic material accumulates strain from the moment a stress is applied, because it is independently deforming, it can deform independently this spring. The deformation of the spring does not depend initially on the deformation of this viscous element, right. So, it deforms immediately the moment a stress is applied, first elastically, and then it goes to gradually in viscous manner. So, therefore, for a short duration of deformation, this system works as an elastic body, but later this goes to a viscous manner. So, this short duration of deformation in most of the cases is recoverable, because then it is independent of the dashpot, but the spring then only plays the role. However, for long term deformation, the viscosity component takes the lead, right, because then viscous material starts flowing through the porous spaces of this piston, and then it remains permanent, and if it becomes permanent, then your deformation is permanent and you cannot recover it. Or in other way, you can recover the deformation of the spring, but you cannot recover the deformation of this dashpot. So, the total deformation therefore is not coming back to its original position once you release the stress. So, the deformation is not totally recoverable, and this is the physical model of Maxwell rheology, where you can arrange it a spring and a dashpot in series. Now, once we do it in series, the equation is very straightforward. So, total strain rate is the sum of the total strain rate of elastic and the total strain rate of viscous components. And if we expand this equation or resolve this equation, then it takes this little complex shape. And here again we have sigma and time, and here we have again strain and time curve. And what we see here, let me explain it, I should do it before, that we have 0 stress, no strain. Then instantaneously I apply the stress, the strain increases instantaneously because of this elastic element. So, this deformation is essentially because of the spring, this one. And then I add the viscous part when I keep it for quite a long time. So, then viscous strain increases slowly. Now, when I release this stress instantaneously, the elastic part released, but the viscous strain stays, it does not come back to its original position. But again this happens very, very slowly, however in linear manner. So, this is viscoelastic rheology, and we learned that we have Maxwell rheology and we have Kelvin rheology. Maxwell rheology, when we add viscosity and elasticity in series, and Kelvin rheology when you add viscosity and elasticity in parallel. Let us talk about another one, which is elastoplastic rheology. The elastoplastic materials, as you can guess from this name, that it combines elastic material, elastic element and plastic element, right. So, it considers recoverable elastic strain from the elastic element, but non-recoverable strain from the plastic element. So, therefore, the total deformation is not recoverable. The permanent deformation, as I talked, is plastic, but it does not begin until the yield stress is reached. Release of stress recovers the elastic component of the total deformation, and the physical model, we can, in a simple way, we can see it when we add them in series. Here I have this spring block, here I have the spring block, and then I have the friction block here, and if I pull it, the spring, then the spring slowly expands because of the force I am applying, and when this spring also gives the load to this pulling load to this friction block, and when this friction is overcome by this force, pulling force, then this friction block starts moving, and when the stress is released, then the spring comes back to its original position, but not the friction block. So, we can have an idea of this behavior from stress versus time and strain versus time curve. So, here when the stress we apply, there is no stress, there is no strain. Then I slowly pull this spring. So, I increase the stress, strain is also increased linearly the way I increase the stress. But then when I start moving this spring, so this is your elastic, sigma y is your yield stress, then this friction block starts moving, and if I release the stress, then the elastic strain I recovered I can recover the elastic strain, and then the plastic strain continues. So, this strain is equivalent to this strain. This is your plastic strain which you cannot recover. This model has significant applications, or it is in a simpler form. We apply it mostly to predict the or understand the behavior of the earthquakes, and we will see it later. So, now we will see what is viscoplastic rheology. As you can understand, it has viscous element and plastic element, and in this case the viscoplastic materials display the linear viscous behavior only above yield stress of a plastic material. Now, viscoplastic materials are also known as Bingham materials or Bingham plastics, and a typical viscoplastic rheology is generally shown by the parallel arrangements of friction block and dash pot, which is shown here. So, what is happening in this case? If I add if I try to understand these two illustrated plots, this is sigma versus time and strain versus time. So, in the stress is 0, strain is 0, and then I start slowly applying the load. Once I am applying this load, interestingly I cannot move the dash pot till I reach the yield of this friction block, right. So, there would be no deformation, there would be no strain even if there is some sort of stress, and when I reach the yield stress, then I instantaneously move this spring block, and then stress goes this way, and then I leave the stress. So, in the entire time the strain continues increasing, but does not matter if I release the stress, the strain remains permanent because of the friction block and also the viscous element. So, I repeat, the viscoplastic materials display linear viscous behavior after the yield stress or only above the yield stress of a when you are dealing with a viscoplastic material. So, therefore, if I do not look at this part, this behavior is essentially a behavior of linear viscous rheology. Now, we will see 3 examples of where and how in large scale processes we apply this complex or combined rheology. The first one we take over is earthquake mechanics. Now, we know how earthquakes do happen, right, that most of the earthquakes do happen along plate boundaries, or to be very specific, in the convergent plate boundaries, where oceanic plate goes down below the continental plate. And here is an illustration where this oceanic block continues to subduct under this continental crust. And we know earthquake happens somewhere here, what we call Benioff zone, at some depth. So, at this place there is a significant amount of friction. So, there is some sort of resistance. Now, when this block is continuously pushing to go down, because of this resistance it cannot move immediately if there is no creep happening. Now, in such a setting, at this region, this plate is accumulating a significant amount of elastic strain. Now, at one point of time when you accumulate this elastic strain, it releases very suddenly in a very similar way we have seen in our friction block, right. So, you overcome the yield stress and then it starts moving instantaneously. So, when this strain here, elastic strain here is released, it released in forms of catastrophic or co-seismic event, and therefore, we have an earthquake. Now, this we can very simply model using this elastoplastic rheology. I just remind you that actual process of earthquake or microphysics of the earthquake is extremely complex, and it's not always advised to explain it using this model, but this is the simplest way you can explain the earthquake mechanics in rheological context. So, what we see here, I have tried to provide here an illustration. So, what we are considering, that this spring and the friction block together form the elastic plate. The pull I am applying to this spring is the plate velocity, and this frictional interface is your contact between continental plate and oceanic plate. So, at T1 things are very stable. Now, the plate velocity has been applied to this spring. So, spring is slowly expanding, as you can see, and when we overcome this frictional resistance here, this block suddenly moves to its forward, it moves forward suddenly, and that happens at T5. And when this sudden move happens, you have a release of energy, and this is an earthquake. Interestingly, when that happens, it actually shrinks the spring back to its original position. So, I have this spring here and I have the spring here. So, I have accumulated the strain, but my elastic element comes back to its original position, not the plastic element, but plate velocity continues. So, the same thing do happen here. I am again stretching the spring, again stretching the spring, again stretching the spring, and again when I reach the elastic this friction of this block, then this block suddenly moves forward and produce another earthquake, and so on. So, I have one earthquake here, I have second earthquake here, and in a similar way I have third earthquake here with accumulation of more strain, and it is happening in a zigzag manner, like it takes time to accumulate the strain, then suddenly it releases, then again it takes time to accumulate the strain, suddenly it releases, and so on. This is very similar of what we call earthquake recurrence, that in a place if you have an earthquake, then it comes back in time. That could be in 100 years, 200 years, or several million years. It depends on the frictional resistance, it depends on many other parameters, the composition, the fluid content, and so on. We are not going to that part, but this behavior of an elastoplastic body is excellent to understand, or to primarily first order understanding of an earthquake phenomena. So, you can see that you have doing elastic loading in the stress, and then at T5 you have a stress drop because the spring comes back, then you have again elastic loading, you have stress drop, each stress drop is characterized by an earthquake. So, this is a very simple model, but one can understand the earthquake mechanics using a very simple combined elastoplastic rheology. Let us have a second example, and this example is from 2002 Denali earthquake. The magnitude was 7.9. It was a huge earthquake, but it happened, you know, Denali is in US, the northern part of US in Alaska. No one died, but it was a devastating earthquake. Close to 50-60 billion was the damage that happened in this earthquake because of many landslides. So, this diagram here on the left side shows the displacement of this earthquake, the maximum displacement. So, this is where the line of the sleep. So, you had this magnitude of this is your magnitude of maximum sleep that happened in this earthquake, which is pretty high in terms of this earthquake that happened on the surface, because this was a very shallow earthquake. It was if I remember correctly 12-13 kilometers depth it happened from the surface. Now, what is interesting of this earthquake? Now, if I have an earthquake, the earthquake is not an isolated process, because the top part of the plate is also attached to the mantle below, which we have learnt is somehow viscous. So, when you have this huge displacement of several kilometers of these plates, then mantle also gets affected by this deformation. So, instantaneous deformation of this crust that produced an earthquake also provide an instantaneous deformation in the mantle, and this is what is shown in this diagram. So, this is a co-seismic stress change. What we see here, that this is this yellow, then orange, then yellow, then green. These are your stress accumulation immediately after the earthquake. And then the second illustration shows the same place after 2 years, and we can clearly see that, at least visualize. I am not going into the detail, but if you are interested, you can read this paper, Friedel, 2006, I think 2006A, they have 2 papers on this. So, what you can see here, that the just if I consider this affected area or affected depth has reduced from the co-seismic time to next 2 years. And this third is showing the change of stress. That means, if you subtract from this to this, and this clearly indicates that we are recovering the stress, and this is an excellent example of Maxwell rheology, that when you have instant deformation, like then the spring takes the lead, but in long term the dashpot comes into the picture to recover or not recover the strain and so on. So, this is an excellent application of viscoelastic rheology in explaining earthquake processes in earth, particularly the mantle deformation during the earthquake. The last example that I would like to give is related to deglaciation and rebound due to deglaciation. Now, we know that most of these lands, that the continents are under the threat of the sea level rise, but there is one place in the world where sea level is going down. Now, this is very interesting, and this is a very important geodynamic problem that people had to solve, and it has been solved again by the study of complex rheology or combined rheology. So, that land is rising, sea level is lowering down. It is the only phenomena that is being seen in Scandinavian parts. So, it is Norway and other places, Finland, Norway and these places. But however, the observation suggests that the sea level rise phenomena is also there. So, with respect to the center of the earth, if we measure the sea level at different times, then sea level is certainly rising in this region. But interestingly, the rise of the land is faster. So, therefore, the relative rise of land we can see there. Now, what do we see? Let us have a first look in this image. At the core of this area, so this is the Scandinavian countries, and these contours that we see here, these are your land uplifts. So, at the core, the land uplifts with a rate of 9 millimeter per year, and then it slowly reduces to 0 almost when you reach the sea. Now, this is explained by a combined rheology, this behavior, that why land is rising up in this region and why also the maximum rise is at the core of this area. So, these 4 diagrams actually very simply describe how this can happen. So, when we have a very standard setting. We have sea, we have crust, and below that we have mantle. So, this part is, you can consider this is your thick continental crust, you have thin oceanic crust, above which you have the sea, and then below you have mantle. Everything is rest and everything is in peace. But earth is a dynamic system, so probably during some sort of cooling age, cooling time, the sea level dropped because it contributed to the formation of glacier in this region. Now, this glacier, which is this blue area, is heavy ice. So, ice is loading the continental crust, and therefore, it is deforming elastic way the continental crust. So, it is going down. Now, it continues the glaciation, and then the size or volume of the glacier increased, therefore, weight also increased, and the continental crust deformed further. Now, when it deformed further elastically, of course, it has to displace the mantle below. So, the mantle below very slowly move away from this place, because it has to accommodate the sinking, elastically sinking continental crust. Now, till this part it is fine, we had glaciers in Finland and Norway, very good. But later, when the deglaciation started, the sea level rise happened, because the water from the glacier goes down, comes back to the sea. So, the elastic deformation that we had in the continental crust is now recovering the strain. So, it is coming back to its original position, and the mantle is also coming back to recover or to fill up the gap. So, this is exactly what is happening, that due to deglaciation, this continental crust is coming back or pushing up, and this is happening mostly because the deglaciation, also the push from the mantle below, and this is also an excellent example of using combined rheology in explaining the rebound due to deglaciation in Scandinavian places. We are almost at the end of the lecture and of this rheology, and I would like to show you one of the first slides where we have cited some of the everyday use of rheology examples, like the ballpoint pens, then why do you have to shake the bottles of tomato ketchup, or running on a beach is harder than running on roads, and so on. Now, I request you to review all these questions or all these facts, and I am sure you can now answer them, or you can now understand the processes of all these mechanisms in terms of rheology. So, I repeat, whatever we do, most of the things where we have some sort of forces required to move something, the best way to explain is using the three basic rheologies or combinations of them. So, with this I finish this lecture, but we are not done with rheology. We will have a short lecture to understand that what are the influences of the different external parameters in governing the flow or strength of the rock. So, we are going to learn it in the next lecture. Thank you very much.